So I hope this will be a bit of discussion also. I'm not going to talk for a full hour, maybe a half of that at most. So I'm going to reflect a little bit about Bode. I'm going to prove the Bode sensitivity integral in two different ways. And then I'm going to talk a little bit about the consequences and some recent work or more recent work about these implications. But let's start from the beginning. I'm last night and I was trying to find Bode's integral in this picture of the curtain that I took, and it took me a little bit a while, and then I saw it. Actually, it is on the curtain. I think Henrik Sandberg is the one who drew it there. So this is what Bode's integral state. It says that we have a function S, which we will, the sensitivity function, which if we take the logarithm of that and we integrate it from 0 to infinity, it vanishes. That's what it says. Of course, I will come back and talk much more about that. But let's start with a little bit historical reflection about this amazing guy, Henrik Bode. So he lived in the beginning of last century. He was growing up in Midwest, but went quite early to the East Coast. He started at the famous Bell Labs just after his master degree. And actually what was interesting already at that time was that he then took a break from Bell Labs, or if Bell Labs actually supported his PhD. So he went to Columbia University, did a PhD in physics, 1935, and then came back to Bell Labs. Then he joined Bell Labs, have a mathematical research group, a math group, which has been very famous for many people who were there and their contribution. And he stays there, and he even took the leadership of that math research group at one point, and then he moved further up in the hierarchy, and he was in the leadership of Bell Labs in general in the end of his term there. So he retired from Bell Labs at 62 years age. And I can maybe say also that Bell Labs basically started when Bode came to Bell Labs. So he was there quite significant time. And then after his term at Bell Labs, he went to Harvard and he became a professor there. Not so much in control, more he was doing systems engineering and so on, and was a professor there teaching for a few years before he left. So what did he do in his career? I mean, he's famous for his early work on network theory, telecommunication, and a number of control problems that he worked on. And he was very active during the Second World War on, for instance, something called the artillery fire control problem. So you wanted to automate cannons basically shooting down things like the missiles and so. And actually he designed a system that was used in London to shoot down the V1 bombs that the Germans were sending over London during the Second World War. For us in control, what is he is very well known is, of course, for the Bode plots. He was the one who introduced these frequency plots that we are teaching in our basic control course, and concepts like gain margin and phase margin and so on. He published a number of very well cited papers. Most of them, as you might know, there was this Bell Labs journals coming out, and most of them are actually in these journals. But you have a classical book, Network Analysis and Feedback Amplifier Design, which I will come back to in the very end of my talk. But it's really a classical book in the area of control. What is fascinating by him was that already at that point, so almost 80 years ago or so, he was one of those who had an integrated view of information communication and control. So a bit like sometimes we attribute to Shannon as well, or to Wiener or so. And it's quoted, actually, he got tons of very nice awards, like the Edison Medal, and you see that was for contribution of communication, computation, and control. So it sounds almost like he could have had a career in modern times now. He was also very broad, as you can see there. He was not only a fellow of IEEE, but also of the American Physical Society, the American Mathematical Society. He also, I mean, the second part of his career, he really, as I said, he took up a leadership position. So this was an interesting photo I found out. So this is from '58, and he was then on this special committee on space technology. So as you know, in the United States, they started this space race. So this committee was the predecessor to what later on became NASA. So he was on the leadership of that. And actually this famous Werner von Braun is there in the back, this guy there. So that was this German who was involved in actually designing this V1 and V2 bombs, one of these thousands of German engineers that the Americans took over to US after the Second World War. That was a little bit about Bode, but let's now come to automatic control. So to appreciate the Bode's integral, you have to know one slide of the automatic control basic course here. So I hope my control colleagues excuse me. So we have the diagram that you see up to the right. So the classical feedback control diagram. So what is control system design about? It is that we have a plant P, which is given as a rational function expressed in the Laplace domain. And then we would like to find a controller C here, such that the closed loop system fulfills some specifications. And these specifications are typically expressed in a function which we call the sensitivity function, which is given here, and in the complementary sensitivity function, which is given here. So what should these two functions, they depend, of course, not only on the plant, but also on the controller C that we are designing. What would we like them to behave like? Yes, as you see up here, the sensitivity function is the how the disturbance D would enter Y. So we would like that to be small so that the output of the system is not affected by disturbance. And similarly, the complementary sensitivity function is the transfer function from noise here, measurement noise, to the output. So we want that also to be small. But now, as you see, if we take S plus T here, it will be 1 plus PC over 1 plus PC, so it's equal to 1. So we have a little bit of challenge, because for any frequency omega here, S plus T are always equal to 1. So that means that we cannot make them small. We cannot fulfill that simple specification that I expressed up here. So what do we do? And you basically take the basic control course and learn how to do design of controllers in the frequency domain. So what you do is that you say that, okay, let's make the sensitivity small at low frequency. So that means that if we have disturbances, we have low frequency disturbances like a set point disturbance, then we will be able to attenuate that by having the sensitivity small at low frequency, or a high low gain, as I showed here. And then we let T be small at high frequency. So we attenuate noise. We say that measurement noise are high frequency, relatively speaking, and then we are able to attenuate that as well. And that means that typically you get sensitivity functions that looks like this, and complementary sensitivity function that looks like that. So that's enough of what you need to know for this talk of basic control. Now to the result of Bode. So Bode proved this result here. So we say that we now have this loop gain, as I said, L of S. We assume that that is a transfer function, and that this has a relative degree of 2 or larger. And then we assume that the closed loop system is stable. So S has no poles in the right half plane. But the open loop system can be unstable, and it has poles now in P1, P2, up to P2. then it's so that sensitivity function that we introduced up here, right? That sensitivity function need always to fulfill this integral. So the integral over the logarithm of the sensitivity function over the frequency span needs to be equal to this constant. So if we have no right half plane poles of the open loop system, this will be equal to 0, and it needs always to be equal to 0. If we have some unstable poles, we get the constant there instead. So this is something fascinating. So this is a conservation law for feedback. So this tells us that whatever we do with feedback, this quantity always needs to be conserved. It's also called the waterbed effect, because what does it tells us? If we look at the sensitivity function again, we see that if we have this red sensitivity function, if we push it down at low frequency, it necessarily needs at some point to pop up. And if we don't push it down so much, like the green one, it doesn't have to pop up so much. But basically the sum of what is above this 0 dB line needs to be equal to what is below that line. So that is what Bode is telling us here. And what are some consequences of that, or how can we reflect on this? Yeah, one thing is, when I talked about the control design problem in the beginning, we should choose C here. We see that this integral now tells us what is possible. So there are fundamental limitation of achievable control performance, what we can do with control, which might seem to be natural, particularly if you are in communication, because the most famous result in communication is probably Shannon's result on the fundamental limitation of achievable channel capacity. How much information can you communicate over a digital channel? And that was actually Mikael Skoglund's Curtian talk. He talked about that. From a control viewpoint, what is a little bit fascinating is that even if Bode and Shannon lived about the same time, and they even wrote some paper together, Shannon's result formed the basics of communication, and many people have been working on that, on that capacity and so on, while this Bode's integral haven't been really considered for a long time, for some reason which is a little bit hard to understand. But one can say almost like it was rediscovered in the 80s in the way I'm presenting it here today. So during the 60s and 70s, there was a lot of state-based method developed, LQG and other types of automated design methods that was very much focusing on how do we do better and better control design, not so much about what can be achieved. Freudenberger and Doug Luce, so Jim Freudenberger is the University of Michigan, they wrote some papers in the early 80s and a very nice lecture note, Springer Verlag lecture notes in 88, where they derived some of these implications of Bode sensitivity integral along the style I'm talking about here. These problems got very much publicity by the first Bode lecture. So to give the Bode lecture is one of the nicest awards in the Control System Society. And the first one who gave a Bode lecture was Günther Stein. He worked his career at Honeywell, where he worked on aircraft control system. And I have quite some material from his work here. So he gave that lecture 89, it's recorded, it's available online. And he also wrote a little bit later, or much later actually, a Control System magazine paper, which is also a very nice paper here. And I've taken quite a few pictures from that paper. But basically, his point and the point I'm trying to make here is this thing about that, it's one need not just to have a sophisticated machine here to do some sort of very advanced type of computation to come up with a controller, but you have also to understand some basic principles on feedback and information. Okay, so let's switch pace a little bit. So let's prove this formula. And I want to ask you both to prove it here. I actually wrote it down on my slide. So it's an exercise in complex analysis, analytic function. If you have seen the Nyquist, how one proved the Nyquist criterion, it's a little bit similar flavor mathematically, but let's just go through it. So to simplify the proof, we assume that we only have one unstable pole instead of a number of unstable poles pk here. So let's say we have one such pole. I put it here, as you see, along the real axis. And then I form a curve. I call this curve B here, that encircles everything on the right-hand side except of that pole B in this way. Now, if we consider S, or we consider logarithm of S, that is an analytic function inside B here. Since it's an analytic function inside B, we know that when we integrate around B here, this integral that we have, this circular integral that we have, logarithm of S here, needs to be equal to 0. That's what Cauchy tells us. Okay, so what can we get out of that? So now what we do is that we take each piece of this curve B here and consider and reason a little bit about. And the first part is this big arc that we have here to the right. So if we integrate over that and we let R become very big, what happens then? Yeah, now we assume that we have relative degree of the L here of 2 or largest, which means that the same thing applies to S, right? So then when R becomes very big, this becomes very small and vanishes. So it basically means that we don't have to consider the integral along the big arc. Instead, we have 3 other pieces left. We have the pieces along the imaginary axis, these 2 pieces, and then we have the piece which is this small part just around P, which I have magnified to the right here. So we should integrate along Roman 1, Roman 2, and Roman 3 there. Okay, so what can we do next? So what we do now is that we factor out that unstable pole from the sensitivity function. I didn't point that out, but let me just remind you that the unstable pole of the loop gain L here, when we have 1 over 1 plus L, that unstable pole will become an unstable 0 of the sensitivity function. So that means that I have a factor of the sensitivity function which is equal to S minus P. So I then write S as S minus P times S star, where S star now would be an analytic function in all of the right half plane. So I can write now the integral of that curve C as the integral over that S minus P part and the S star part, as you see there. And then we do these actual computations. And that would have taken me another slide if I should do them explicitly. So I didn't do them here. For those of you who studied analytic function, complex analysis, residue calcul, you might remember that when you integrated over this type of zeros of the functions, you then get something which has to do with how many revolution that you do. So basically that first integral that we had will tend to 2 pi times P, which is a pole, times J, which is the square root of -1 here, right? So this we do. S star, now I said that would be analytic, so it's not surprising that if we let epsilon go to 0 here, that would actually tend to 0, but of course one need to prove that. So if you plug these 2 things together there, you see now that the integral over ln S would be 10 to this quantity minus 2 pi pj. So this means now that what we end up with is that the sum of these 2 integral over the negative imaginary axis and positive imaginary axis will be equal to that quantity. So what is left now is just to see that the left-hand side is equal to that integral of a logarithm of the magnitude of S. And that's just a few steps of analysis here, which you see is straightforward. So that would now gives us this result for a single pole P. If we would have multiple poles that we have in this expression, what we would have instead is that we would have to create a little bit more complex curve, right? So we avoid each one of these poles independently, but otherwise it looks just the same. Remember also that if we don't have poles purely on the real positive axis there, but they are complex conjugate, they are always conjugate, right? So when we sum them up, they will end up, the sum of two such poles will always end up on the positive real axis. So that's how this result is proved. So when I went through this proof and so on, I find also this publication that shows another proof, which I never saw before. But if you don't like complex analysis, you can actually prove the integral formula just by using various type of existing integral formulas. So you basically then write out the rational function that S corresponds to, and you introduce the zeros and poles of the component, the numerator and denominator of that function, as you see here, and then you can express that in the poles and zeros that you get, and you're only interested in the unstable poles here, so you end up with now the same expression that we had previously. So that was the proof. Let's now talk a little bit about the consequences of this formula. And the consequences is not clear from the formula, right? If we now have unstable zeros, right, half-plane zeros or non-minimum phase zeros, or we have unstable poles, they make systems fundamentally hard to control. We maybe don't see it directly from the formula, but I will show how, or illustrate a little bit how it can be derived from these formulas. And yeah, I showed just the sensitivity formula. There is something very similar one for the complementary sensitivity, which includes the unstable zeros instead. But from these formulas, as well as from the definitions of phase and gain margins, you can now derive explicit conditions, which shows you how hard it is to control systems with right half plane zeros and poles. And let's look at a few of these expressions here, and these are taken from Åström's a paper he wrote on this topic 20 years ago in the European Journal of Control. So what can you say now if you have a plant you are controlling and you have one non-minimum phase zero? Yeah, so in that case, what we can, for instance, express the limitation on from that zero is if we look at how the sensitivity function must look like and what is the implication on the loop gain. And the loop gain, as I showed previously, typically look like you see here. It has to be high at low frequency. It should go typically around a slope minus a half through the crossover frequency. And then it should decay a little bit more rapidly after this. So if we, so to say, use this in the design and we then fulfill some robustness margin expressed in the phase and gain margin here, we can actually compute what implication this have, this non-minimum phase zero on the crossover frequency. So here we can show, for instance, that the crossover frequency must be less than that non-minimum phase zero if you want a certain phase margin. And very similarly, if we instead have an unstable system, So now you have a factor in the plant which is unstable. Then we can get exactly the opposite result, saying that the crossover frequency means to be higher than where that pole is located. And notice that these consequences are quite natural. So if we have a zero which is in the right half plane and it's rather slow, you can compare that with having a system you are controlling which have a bit of a delay. And if you have a delay, you cannot use very high gain when you're controlling that. So that would give you a problem. And a bit similar, if you have an unstable system that you are controlling, you need to rapidly control it. You need to have high gain. So it's natural that we do it. But of course, out of just this back of the envelope calculation here on right half plane zero and poles, we see that we could get into problems. What happens if we have both? So if we both have a right half plane zero and a right half plane pole, we can get into situation now, depending on the ratio of the zero and the pole, where we cannot get any phase margin at all. So which means that we basically cannot robustly stabilize the system. So, and remember that the bad thing is to have P large. P large means that we have a fast unstable pole. Bad thing is to have the zero close to the origin, so Z small. So this means that the difficult part here is the 2, for instance. That's impossible because phase margin is -6 in this particular case. If it's larger here, it becomes easier. But you see, we can compute this in this case. And a classical example we use when we teach this is the impossibility to actually balance a short inverted pendulum in your own hand. And as you know, you cannot do that with something as short as a pen. It's impossible. And this is basically the proof for why we cannot do that. So does this type of result, do they have any practical implication? Yes, that was exactly what Günther Stein showed in his Bode lecture. He took a couple of examples to show this. One that he has personally been involved with. You might have seen this airplane. It was a research airplane that was developed by the US Defense Agency called X-29. It was on purpose designed unstable and had this particular forward swept wing formation. Of course, depending on the operating conditions, so what speed, what height, and so on, you have different dynamics. But under certain operating condition, you get something exactly like in the case we saw on previous slides. So you have an unstable zero, you have an unstable pole. So there are limitations to what you can actually achieve by control design. But what was fascinating with this particular system was that there was somehow a competition. There were several design groups, industrial groups that worked on the control design. And there were apparently a heated debate about which method was best and who could design the best control and so on. And it was only late in this phase where actually this was realized that the specification that one tried to achieve was impossible, and one actually could prove that they were impossible. Another a little bit similar situation we are all familiar with is the Chernobyl disaster. So what was particular about Chernobyl was that under certain operating condition there, this plant became unstable. You might have seen this if you watched that recent movie about the Chernobyl accident, that there was this experiment being done in Chernobyl where the feed water, so these are the actual curves from the operation of Chernobyl, and you know you need water in the to avoid really like the reaction is not taking off too much. But what they did was that during this manual experiment, they inserted the control rods and they lowered the feed water. So they created a situation which was okay, but the problem was that they then removed the control rods. And so they were down with very, very low power production in the system. So the top plot here is over some minutes, and then we continue down. Here you see the power. There were basically no power production, but the control rods were almost out of the plant. And then they realized that something bad was going on, and they tried manually now to start injecting the control rods into the nuclear reactor again. But there was limitation with the speed which you can enter these rods into the reaction. And you see here that they are entering in the maximum speed, but that was not enough. And then the reaction took off here, and we see a perfect exponential function happening here just before the whole thing exploded. So it's another illustration about how critical it is if we have saturation limitation, which we basically always have under instability. And actually the name of the paper that Günther Stein wrote for the Control System magazine is called this, Respect the Unstable. Okay, let's jump to two other things I would like to talk about. One is not Bode's sensitivity integral, but Henrik Sandberg's sensitivity integral. So it's Henrik, our colleague. I don't know if Henrik is here today, but he actually wrote a very nice paper as part of his thesis work on extending Bode's integral to time periodic systems. So what is a linear time periodic system? Yeah, we can express that in the impulse response of the system. So we say that we have a linear system given by this expression here, but the impulse response G now is periodic and have periodicity capital T. If you have such a system, you can take the Laplace transform and you can define now a transfer function for that system. The transfer function will not be as the usual transfer function we are used to, but it will instead be an infinite dimensional transfer function. It's called the harmonic transfer function. So you see you have an infinite matrix basically expanding in all directions of this Laplace transform of the impulse response up there. So what one I can do is to express with this transfer function, we can compute the sensitivity function and then express the sensitivity integral in this form. So that's basically what it says here. So we have now a sensitivity operator that we consider. We have to assume, just as previously, this is stable. And if it is, then we have a sensitivity integral, which looks very similar to what you have seen before, right? Now it's multivariable, so we have a determinant there that operate on this. And then we have the integration over the half of the frequency that of the period that we have. So this is much harder to prove than Bode's sensitivity integral. So I won't go through the proof. Basically, there are two things here which are difficult. In the Bode's case, remember that we needed that the relative degree now of the loop gain of the plant, G, if you want, had to be 2 or larger. What does that mean? The relative degree when we now have this harmonic transfer function. So I need to define that in a proper way so that when you now integrate and you go to infinity, this is well positioned, well posed here. And the same thing is also about the closed loop system here. You have to be a bit careful. But basically, otherwise, the interpretation of this sensitivity integral for periodic system is very similar as before. So for instance, we have now the waterbed effect that we can express through this operator instead, this sensitivity operator. Just as you saw previously, if we push it down at some frequency, it needs to pop up at other frequency there. Okay, let's look at some other limitations, a similar style as the one that you saw Åström derived earlier there. how one can sort of extend some of what you have seen previously to MIMO system and express them in the time domain. So to appreciate this, we need to just remind ourselves what is a zero and a pole of a transfer function matrix. Yeah, so zero is something which, when we plug it into the transfer function matrix G here, it vanishes when we take a constant vector psi and take the scalar product with that matrix. And we call now Z, of course, we call the zero in this case. The psi here is then called the zero direction. So for MIMO system, a transfer function matrix or a plant here G always have a zero together with a zero direction. And very similar, we can also define now poles by looking at the inverse then of G, right? We have a pole and we have a pole direction. So let's do a very simple computation on this, on the complementary sensitivity function that we have. So if I now write out what is the complementary sensitivity function T, so for a multi or a MIMO system, I will get this GC and then multiply by the inverse here of the sensitivity function. And then if I plug in the zero Z here, right? And I multiply by psi transpose, this first part here vanishes. So the right-hand side become equal to zero, which means that when I multiply also the complementary sensitivity function by psi transpose, when I evaluated a Z, that is equal to zero. Now I can plug in the definition of these Laplace transforms evaluation that I have. And let's say that I do that when I'm hitting the system with a step. So I take now a step R and I multiply the left-hand side here from the right with R. In that case, I will get an output Y, the Laplace transform of that output. So I get psi transpose Y. But then I can use the definition now of the Laplace transform. So I use the definition of Y of Z, and that is equal to this expression. So you see from that calculation that when I take psi transpose and multiply that with this integral, it has to be equal to zero. So for any response I have here, I get some sort of a little bit similar like the previous integrals. I have integrals here which are independent of the controller I use. They depend on the right-hand plane zero. So there are some connection by this integral here, how psi transpose the direction of the zero, and the output of the system, how they are interconnected. So this we can now, for instance, by approximating the integral that we have here, we can derive some results which are easier to interpret and work with to see what type of set point responses Y we can actually get. And if we do that, we get the theorem. And so the theorem here states the following. So if we now have this G with a right half plane zero, Z, and direction psi, we have a relation. So you look to the left of this inequality, what you have here, you have a psi, and then you have the overshoot of the response, sorry, the undershoot of the response. You have the interaction to the other output of the system. So we say something here like the undershoot in one channel in Y1 and the interaction with the other output, so Y2 here, the size of that. These two quantities needs to be greater than larger when something we have on the right-hand side. Epsilon on the right-hand side is just the ringing effect that we have. So let's say that we put epsilon equal to 0 here. Then you see that you get something on the right-hand side, which is just 1 over e to the power of z, t settling time -1. So when the 0 here when Z here goes to 0, we see that then necessarily we need to have a large undershoot in the system. So Y1U needs to be above a certain quantity, which is given by the right-hand side, in case we didn't have the sum. We didn't have the sum if we have a SISO system. A SISO system means that we don't have Y2 here. So this gives a fundamental limitation for this type of set point responses, what we can achieve and how it depends on the 0. But if we have a MIMO system, we can help the left-hand side, we can help the undershoot here on the left-hand side by actually let there be some interaction instead. So we can have a smaller undershoot here by having a larger connection, so to say, interaction with the other things. There is a trade-off. So in some sense, or in this formal sense, MIMO systems are easier to control than SISO system. So the whole story here works perfectly fine also for right half plane pole with suitable adjustments. So now instead of the undershoot that we get for right half plane 0 for right half plane poles, we get overshoots instead. So we necessarily have an overshoot in the set point response. But otherwise, we have a similar trade-offs that we can do. Expressions are different, as you see here, but there is a similar type of interpretations that we can do here. Okay, so with that, I just would like to come back to Bode here, because I'm not sure if this was a legal archive or not on internet, but I was very happily surprised to seeing that it was possible to actually read this book on internet. So it's available on the link there that you get to if you Google the name of the book. What is very nice when you go through the book is that a few things one can reflect on. You can read the preface, which gives actually some historical vibrations here. So I mean, basically, this whole text was developed as a course that he were given at Bell Labs and also to other labs in the United States, more or less during the Second World War, and was very much towards, so to say, improving amplifier design and so on that was used in various applications. The book is contain both a lot of mathematics. There are theorems for various type of things, a lot on complex analysis and so on. So it's clear that he has a mathematical training. It's very obvious, but it's also a lot of hands-on things. So the rules of how to draw Bode diagram and tons of different diagrams and so on are available in there. You don't see so much discussion of Laplace transform and so on. You see more discussion or of course any computations. It's much more on the design of amplifiers, a lot of electronic circuit and circuit designs and so on. But if you have some time over sometime, please go through and have a look. It was a very nice book. Okay, Arvin, so with that that was what I was going to talk about. I'm happy to, if there is someone who have some questions or comments.